Alright guys, I've already started recording, so just to give you guys a heads up of what is to be expected for this week. So um, today we're going to finish up our unit on thermodynamics. Remember we started thermodynamics several weeks ago, and thermodynamics basically dealt with, heat, energy, temperature, things like that. So we're going to finish up that unit today. And just to let you guys know, at the end of this week on Friday, you're going to have your fourth 6 weeks test. Okay, so your fourth 6 weeks test will be on Friday, and the topics covered in the fourth 6 weeks test will basically it will basically be information from our momentum unit and our thermodynamics unit. Okay, and we're going to have a review on Wednesday. So today we're going to finish up thermodynamics. Wednesday we review, and then Friday is going to be our test. Okay. So just so you guys know that. Okay. Let me share my screen just to show you guys what's in Schoology. Okay, so mainly what I want to do today, today is going to be highly conceptual, and that I'm just going to go over the laws of thermodynamics, uh, and then I'm going to let you guys get started on this assignment, okay, that I have posted in Schoology. So it's the fourth 6 weeks. Today is February the 2nd, and it is a Monday. Okay. So this is what we're going to talk about today: the laws of thermodynamics. Okay. So today we're going to focus on what is known as the zeroth law of thermodynamics, the first law of thermodynamics, and the second law of thermodynamics. So those are the laws that we're going to focus on for today. I'm going to go ahead and get started with explaining the zeroth law. The zeroth law is probably the easiest to explain. I'm not going to spend a whole lot of time on this law. I'm just going to kind of explain it, what it is, and then we're going to move on to the first and the second law. The first and the second laws are two laws that I really want to explain to you guys because they're the ones that are the most important. And I'm going to show you guys a few videos of these laws. Okay, so the laws of thermodynamics just deal with heat and energy. Before we get to these laws, I want to remind you guys of something that I stated several weeks ago. So, guys, if y'all remember, several weeks ago, I stated that anytime you have two substances of different temperature and you bring them in contact with each other, energy always moves from the hotter substance to the colder substance. So, for example, if I have, let's say, um, if I have a substance that's um, 98 degrees Celsius, and I have another substance that's 25 degrees Celsius. If I take these two substances and I bring them in contact with each other, remember what we said that the energy will always flow from the hotter substance to the colder substance, never the other way around. Energy always flows from hot to cold. So guys, remember that because that's going to be important on the exam later on this week. That you guys remember that principle. Energy always flows from hot to cold, and never the other way around. Um, and so if I take these two substances and I bring them in contact with each other, the energy will flow from the hotter substance to the colder substances until both substances are in thermal equilibrium. Okay, so just something to keep in mind as we go throughout this lesson. Okay, so now let's start with the zero law of thermodynamics. Okay, so um, according to Wikipedia, the zero law of thermodynamics states that if two thermodynamic systems are each in thermal equilibrium with a third one, that they are in thermal equilibrium with each other. Okay, so like I said, I'm not going to spend a whole time on this. Spend a whole lot of time on this law. I just basically want to explain what it is. Basically, what this means is if you have three substances, so let's say I have a substance labeled A, and I have a substance labeled B, and I have a substance labeled C. Okay, and imagine that all three of these substances have a certain temperature. Okay, the zeroth law of thermodynamics says that if the temperature of A is equal to the temperature of C, and if you know that the temperature of B is also equal to the temperature of C, then you can guarantee that the temperature of A must be equal to the temperature of B. That's all the zero law of thermodynamics states. It says if you have three substances and two of those substances are in thermal equilibrium. So, for example, so if A is equivalent in temperature to C and B is equivalent in temperature to C, then you can guarantee that these two substances have to be in thermal equilibrium with each other. Okay, that's all the zero law of thermodynamics states. It's just a statement on thermal equilibrium. It's almost stating the obvious. Okay, um, the zero law of thermodynamics. Okay, that's basically what it means. It's just stating that um, that that if two thermodynamic systems are each in thermal equilibrium with a third one, then they are in thermal equilibrium with each other. Okay, that is the zero law of thermodynamics. Pretty easy. What I want to focus on next, I want to focus more on the first law and the second law of thermodynamics. Okay. Um, so the first law of thermodynamics, this law is basically it's a version of the law of conservation of energy that has been adapted to thermodynamic processes. Basically, the law of conservation of energy states that the total energy of an isolated system is constant. Um, in other words, while energy can be transformed from one form to another, energy can neither be created nor destroyed. So, the first law of thermodynamics is just basically states that the total energy of an isolated system does not change. Um, okay, so again, energy may transform, but total energy remains constant. So this law is important because we can mathematically formulate um, how much usable work we can get out of a system if we know how much energy or heat energy we put into that system. So let me show you guys a video of what I mean by this. Videos always help. Videos always help.
Energy is conserved. That is, the amount of energy before will always equal the amount of energy after. Energy, however, comes in many different forms. There's potential energy, kinetic energy, radiant energy, heat energy, and so on. The many forms can complicate its accounting. You might initially fail to identify one of the forms, and voila, you think you've discovered a perpetual motion machine. Such hopes have not withstood repeated experiments, which tell us that energy is always conserved through any process. It can change form, but what you start with is what you'll end up with. Let's look at a simple example to illustrate the point. A utility room with a heater pumps 500 kilojoules of heat into a living room. If the heater delivers 500 kilojoules of heat, the living room receives 500 kilojoules of heat, and no more or less than that. But suppose there's a toy car with a sail by the heating vent. The warm air flowing into the room pushes on the sail, which gets the car moving. A force is applied over a distance, which means work is being done on the car. strictly speaking, the room won't be warmed by as much. Why? Because some of the 500 kilojoules of heat went to pushing the car. Let's make up some numbers here. Let's say 10 kilojoules of the energy went to pushing the toy car. That means the living room only received 490 kilojoules of heat, not the ideal 500 kilojoules. So heat added to the living room equals the heat received by the living room plus work done within the living room. Energy took different forms, yes, but remains conserved. Our accounting is good and none is missing. If we include heat and work in our discussions of energy conservation, then we're into an area of science known as thermodynamics. Thermo means heat. Dynamic means action. So, with thermodynamics, we're talking about actions that involve the transfer of energy, heat. Our example of the toy car in the heated room focuses on what is known as the first law of thermodynamics, which is no more than energy conservation applied to thermal energy. When the accounting is proper, it all adds up. That's good energy. Thermodynamics. If
Okay,
science, thermo means
okay, um, so in this example here, I really like this example because this basically put everything into perspective. Notice how as we pump energy into this room, the total energy stays conserved, even though the energy took on different forms. So, our heater pumped a total of 500 joules of energy into this living room. However, if you notice, some of that energy went toward heating the air. However, some of that energy went toward moving the toy car. Okay, so let me go back to where the toy car was. So, some of the energy went toward moving the toy car. Um, Basically, what thermodynamics says, the first law of thermodynamics says, um, if we know the total energy content, heat energy, that we supply toward a system, in this case, the system is our room, and let's say we have objects in the room that can do work, we can mathematically predict how much usable work we're going to get out of a system, um, and we can also mathematically predict how much temperature change is going to occur in the system as well. Um, Now, why is this useful? Well, it turns out the first law of thermodynamics was very useful for the Industrial Revolution. For example, like guys, imagine a ship. A ship turns heat into usable energy. And you guys are familiar with this. For example, you guys have seen the movie Titanic. Um, in the movie Titanic, um, there's a scene where they go down to the bottom of the ship and they're in the boiler room. Well, in the boiler room, believe it or not, the ship is able to work is because they're using the laws of thermodynamics, the first law of thermodynamics. Basically, they're heating up coal, they're turning that coal into usable energy. So some of that energy goes toward heating up the thermal room, and some of the energy goes toward powering a turbine, so that the turbine circulates and actually, causes the ship, to rotate at the bottom, therefore moving. Okay, so that's why the first law of thermodynamics is useful. We can mathematically predict how much usable energy we're going to get out of a system. I have one more video that I want to show that it makes sense of the first law of thermodynamics, and then we're going to be ready to move on to our second law.
Hello there, it's the Easy Engineering once again, and today's topic is the first law of thermodynamics. The first law of thermodynamics says that heat is a form of energy. And as what all other forms of energy is subject to, it follows the law of conservation of energy. So what does this mean? It means that heat energy also cannot be created nor destroyed and can only be transferred to one form or another. Don't overthink this too much. This law is all about heat as energy and follows the law of conservation of energy. And that's it. Now to appreciate the application of this law, let's try a very good one example. This coal is just a type of rock, right? But for scientists, this rock contains an energy that produced heat energy when it undergoes a complete combustion. Actually, some power plant utilizes this coal to generate electrical energy, or what we call as electricity. What they do is that they feed this coal into a boiler furnace, and with an assistance of oxygen and a little heat, this creates a combustion in a form of heat energy. Now, the heat energy will transfer its energy to water above it, making it into a steam. And the steam will rotate a turbine, and that's a mechanical energy right there. And then, this turbine will rotate a generator, which converts that energy into electrical energy. See that just by knowing this law, you can do so much. And that's it. This is easy engineering. See you again for our other easy and fun engineering topics.
Okay, so everybody got that? That is the first law of thermodynamics. So in this case, we're using heat energy to convert that to do usable work. In this case, we're powering a turbine, which then power a power plant to supply electricity to your homes. Okay, so this is one way to get electricity to your homes by using the law of thermodynamics and converting heat energy into other forms of energy. Okay, so that's the first law of thermodynamics. It's, in a nutshell, it just says that energy, heat energy is conserved. Um, okay, now the last law that I want to talk about today is the second law of thermodynamics. Okay, so the second law of thermodynamics. The second law of thermodynamics states that um, states that there is a natural tendency of an isolated system to degenerate into a more disordered state. In other words, systems tend to become more disordered with time. Okay. Um, another name for this law, guys, and let me write this down. Another name for this law is the law of entropy. So let me write this down so you guys know what this means, and then I'm going to explain it. So the second law of thermodynamics, another name for this law is called the law of entropy. What is entropy? Okay. Well, guys, entropy by definition just means a measurement of disorder, a measurement of disorder. That's what entropy is. Entropy just means disorder or randomness. Okay. And basically, the second law of thermodynamics states that um, uh, things or things in a closed system tend to become more random or more disordered with time. So I'm gonna write that down. Things become more disordered with time, or let me say more random with time, more random with time. So, uh, In other words, entropy increases with time, right? Because if entropy is a measurement of disorder, and disorder increases over time, that means the second law of thermodynamics states that entropy is something that increases with time. Okay, so um, what is it that I mean by this? That systems become more disordered with time? Well, let me give you guys an example of what I mean visually. To give you guys an example of what I mean visually, guys, imagine for a second that I have a room that has 6 molecules inside. So here's my room, and imagine that in the corner of this room, I place 6 molecules in this corner of this room. Okay. So I put 6 molecules in this room, okay, and I just leave those molecules there. What do you guys think will happen over time? Well, remember uh, that if you take a look at any substance that is made of molecules, and you look at those molecules, remember those molecules are vibrating and they're moving chaotically. They're moving all over the place. Well, guys, what the second law of thermodynamics said what it states that if I take these molecules and I leave them in this room, as time passes by, eventually these molecules are going to spread out and they're going to move more and more randomly. They're going to spread out and they're going to become more and more chaotic. So let's say I leave the room and I come back in 10 minutes. I notice that these molecules are more spread out. Um, it may look like this. Um, right? Because remember, these molecules, they're moving all over the place. They're moving chaotically. Let's say I leave the room and then come back in like another 10 minutes. Um, I come back another 10 minutes and I'm going to notice that the molecules are going to be even more spread out in the room. Um, the molecules may look like this. So, guys, this is the second law of thermodynamics in a nutshell. The second law of thermodynamics in a nutshell says that if I have a closed system and I just wait over time, that system will become more and more chaotic and more disordered. So, as we see in this example here, these molecules, if I leave them in this room, they spread out and they move all over the place. They become more and more chaotic with time. That's the second law of thermodynamics. Their entropy is increasing. They're becoming more and more random. Um, uh, that's what we mean by the second law of thermodynamics. And guys, the second law of thermodynamics also says is that this process is irreversible. Is irreversible. Like in other words, you can't expect matter to organize itself over time. Rather, matter becomes more disordered with time. For example, um, okay, guys, imagine this right here. Okay, imagine you have an egg and you take that egg and you drop it. Okay, and that egg breaks. It's kind of obvious to you guys that if this egg breaks, that the the particles are going to spread out all over the floor. But guys, can you imagine a process where an egg can unbreak itself? No, you can't. Like you can't imagine an egg putting itself back together again um, by itself. Um, if the particles have already if the egg is already broken and the particles have already spread out, like that does not happen. That's basically what the second law of thermodynamics says. It basically just says systems do not spontaneously organize themselves over time. In other words, all natural processes are irreversible. That's the second law of thermodynamics. Just like an egg can't spontaneously unbreak itself, so systems don't spontaneously organize themselves over time. And I have one more video that I'm going to show you guys um, on the second law of thermodynamics. Just
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 133. It's on the second law of thermodynamics. First law relates to energy and how it can neither be created nor destroyed, but the second law relates to entropy. What is entropy? It's a measure of the amount of disorder in a process. And so if you watch the word entropy, I'm increasing entropy of entropy. In other words, I'm increasing the disorder. And it's much more likely that it is to fall apart than all those pieces were to spontaneously come back together again. So the second law of thermodynamics relates to processes that can either be reversible or irreversible. Reversible means they can go either way, and the amount of entropy won't change. But in an irreversible process, the amount of entropy will increase over time. Now, entropy is a state function. That means it's just measured at one point or one state in time. It measures disorder. Other alternative definitions, it's the lack of energy to do work. And so a way to think of it is increasing chaos of the system or its organization of the system. The nice thing about AP Physics is you don't have to quantify entropy. You just have to know its quality, in other words, what it is. In a closed system, the amount of entropy will never decrease. It always increases over time. And if we think of the whole universe, entropy of the universe is going to increase over time as well. Now that's kind of a vague concept. What does it mean to increase the entropy of the universe? Let me give you some solid examples. And so I have two videos here, video A and B. Let me start playing them. They're both the same video, but one is played in the forward direction and one is played in the reverse direction. And so can you figure out which one is forward and which one is reverse? It's hard to tell. If I remember right, A is actually played in the forward direction. So we can think of this as a reversible process. It's just as likely to happen in the A direction as it is in the B direction. But let me show you another video. Can you figure out which one of these is played in the forward and which one is played in the reverse? Well, you've probably never seen B as a video. You don't see milk spontaneously move outside of a cup, so you know A is in the direction. Now we're dealing with an irreversible process. It's totally probable to happen in the A direction, but it's statistically improbable, if not impossible, to happen in the B direction. Let's watch this. This is another one. So which one of these is in the forward direction? Well, B now is in the forward direction. And so now we're getting at what it is to be an irreversible process. In other words, in an irreversible process, and I'm just tugging on the block in the bottom, it's moving in that direction. Now, could the reverse occur? Perhaps, but it's going to be statistically improbable for it to occur. So now we've got an irreversible process. What's going to happen to the entropy? It's going to increase over time. And sometimes you'll hear it referred to entropy as time zero. It's going to move in the direction of time in an irreversible process. So let me give you an example of that. On the left, we have gas molecules in a container. On the right, we have those same gas molecules in a container. So which do you think took place first? Which of these is early and which is later in time? Well, the right answer is going to be like that. It's going to become more disordered in time. So what you can do is just draw the arrow of time, and then entropy is just going to be in that same exact direction. And so the second law of thermodynamics says, in a closed system, a system isolated from its surroundings, entropy will never decrease. In other words, entropy is going to increase over time. In other words, in a closed system, as time advances, entropy is going to advance as well. But this might seem counterintuitive. How could I make something like this video and this computer? They seem to have a huge amount of order. They don't seem to be chaotic as well. And so it seems like time and entropy in this case are reversed. Over time, we have something that's more complex. Well, you have to step back again and remember what I said very carefully. Entropy never decreases, but that's in a closed system. This computer and this video are not a closed system. I made them more ordered by making the surroundings less ordered. And that leads into this whole idea that over time, entropy is going to increase in the environment. And so did you learn to connect qualitatively the second law of thermodynamics and the state function of entropy? I hope so, and I hope that was helpful.
Okay, so hopefully everybody got that. That's what we mean by when we talk about the law of thermodynamics. The second law of thermodynamics just says that in a closed system, entropy will increase. In other words, a system naturally becomes more chaotic over time. And the second law of thermodynamics says that natural processes are irreversible, right? If things tend to become more chaotic over time, it's it's not likely that you can get the system to reverse itself and become more ordered over time. Okay? And that's always true of a closed system. That's always true of a closed system. Now, one more thing I want to state here before I leave the second law of thermodynamics is that some of you guys may be thinking, well, and again, he kind of talked about this at the end of the video, but I kind of want to elaborate on it further. Um, can you guys think of a situation in which something can become more ordered over time? Well, some of you guys may have had experiences where you've taken a cup of ice and you put a cup of ice in the freezer. I'm sorry, imagine you put a cup of water in the freezer. Some of you guys may have had experience where, like, if you put a cup of water in the freezer, and over time, that water will become ice. Now, if you guys look at ice molecules or ice particles are highly ordered. So, in other words, you took water molecules and you organized themselves and you formed these ice crystals. So, in this situation right here, guys, did we break the second law of thermodynamics? Because remember, the second law of thermodynamics states that a system should become more disordered over time. But in this case right here, uh, our water became ice, so it appeared we became more ordered over time. Well, the answer to the question is that no, we did not break the second law of thermodynamics. Because remember what he said in the video, the second law of thermodynamics only applies to closed systems. In this case, by putting something in the refrigerator or the freezer, this is no longer a closed system. Well, how do we know that? Because in this case, the freezer takes energy out of the system. It allows the system to become colder over time, therefore the molecules becoming more ordered and more structured. Okay, so we are not violating the second law of thermodynamics in this particular example because the second law of thermodynamics only applies to closed systems. In this case of putting something in the freezer, we're dealing with a open system. Okay, so in other words, we're dealing with an open system in that we're allowing energy to escape from the system. Okay, so just something to keep in mind. All right. So here's what I want to do. So in order to close the class on today, um, I want to go over some of these questions with you guys in the assignment. I'm not going to go over all of them, but I'm going to go over some of them with you all. And of course, the reason for this is because I want you guys to have time today reviewing those test questions that I'm going to post in Schoology, so that if you guys have any questions on Wednesday, you can ask me any questions on the review. But I want to go over some of the questions with you guys. So if you're at your computer, what I would do, I would click on the assignment that says the laws of thermodynamics. And if you guys want, you can work right along with me. Um, they're just 10 multiple choice questions, and I'm just going to go over a few of them with you guys. It's just going over everything that we just talked about. Okay, so guys, go ahead and pull out your computer or whatever electronic device that is next to you, and open up Schoology, and then pull up this assignment. Okay, um, thank you, Devin, for letting me know. Hold on, let me open that right now. I'm sorry, I thought it was open. Give me just a second, Devin, while I access it. Okay, guys, try it again. You should be able to access it now. Just change the setting. Devin, see if you can access it now. Okay, great. Yeah, thank you for letting me know that. I forgot to this I forgot to enable it when I posted this morning. Okay, guys, which law of thermodynamics, and this is the first question, which law of thermodynamics applies to the following statement? A system will naturally tend toward disorder with time. Is it the second law, the zeroth law, or the first law? Should be easy. We just said that this is the second law. Okay, so again, guys, find this particular question, and then you're going to choose the second law. Okay, let's move on. Now, you guys, your questions may be in a different order from mine. If it's in a different order, just find the question as we go to it. So this question says, a moving box slides across the floor to a stop. The box initially begins sliding with a certain amount of kinetic energy, but what does the energy become as it rubs across the table? Guys, this should be obvious here. If we take our object here and we rub it across the table, we're we're converting kinetic energy in the box into thermal energy. In other words, it's becoming heat. It's kind of like taking your hands. If you take your hands and rub them together, you're converting kinetic energy into heat. Okay? So that is that one. Um, what about this one right here? It says if the entropy of an object increases, what happens to the entropy of the universe? Okay, so he just stated this in the universe in that video that the entropy of the universe tends to increase with time. So the entropy of the universe increases with time. That's what the law of entropy says. In other words, the universe is becoming more disordered as time progresses. Move on to this question here. And again, guys, if your questions are out of order, just skip to this particular question. Um, and you can always go back to your other questions. Which law of thermodynamics defines what thermal equilibrium is? Okay, so when we're talking about thermal equilibrium, we talked about this. This would be the zeroth law of thermodynamics. So let's move on to the next one. This one right here, I expect you guys to know the answer to this because we just got done talking about this concept here. Um, so let's move on to this one right here. Okay. Once workable energy gets transferred to heat energy, is it reversible or irreversible in a closed system? Okay. So remember when we see it, the second law of thermodynamics basically says that all natural processes are irreversible in a closed system. In other words, you can't expect an egg to unbreak itself because if you saw something like that where an egg become more ordered over time, that's clearly breaking a law of physics. It's breaking the laws of It's breaking the second law of thermodynamics. Um, this one should be pretty easy right here. Um, this one is easy. Um, this one right here, you guys should be able to do yourself. Look at what this diagram is saying. This diagram is saying that like heat is being transferred from the 15 um, degree Kelvin object to the 25-degree Kelvin object. In other words, guys, this diagram is saying energy is traveling from the colder substance to the hotter substance. Is that true or false? Can this happen naturally? I'll leave you guys to answer that on your own. Okay. So, guys, just go ahead and finish the rest on your own. Okay, are there any final questions for me before I let you guys go? Any final questions for me? Okay, so guys, like I said, just go ahead and finish the remainder of those questions by yourselves to get that submitted. What I'm going to do before the end of the day, I am going to post basically some test review questions. It's not required that you have to go over the test review questions. It's optional. But I do want you guys to have the opportunity to look over these test review questions if you want to. That way, on Wednesday, if you have anything that you have questions on regarding the review, you can ask me on Wednesday, and then we can go over that before you guys have the test on Friday. Um, but if there are no immediate questions for me, you guys are free to go. The YouTube video will hopefully be posted soon. It just depends on how fast my internet is going to work here at the house. But guys, have a good one.